We've seen how to construct suffix arrays in n log n time by a practically efficient and robust method, the fat pivot quicksort. But the theoretical interesting result is that we can do it in linear time in the length of the string, and that's what we'll look at now. Before we can really explain and understand this algorithm, it helps a lot to make this following definition. So remember, the suffix array is this. It's I called it L because it's the leaves of the suffix tree. And we said the rth entry in this leaf array is, well, the rth leaf in the suffix tree, and that has a value I, which means that's the ith, well, the suffix starting at I. The ith suffix in text order is the rth suffix in sorted order. Now I'll define a second array R, which is just the opposite. R of I is R, is small r, if L of R is I. So it's the inverse. That's why it's called the inverse suffix array. And if this is the case, that's the same as saying there are R suffixes that come before the ith one in sorted order. And it's that's the same as saying this suffix ti has rank R, again starting at 0 as always. And from this definition is where this R gets its name from. It's the rank array. But there's also a more figurative meaning to L and R, which is left and right. And this is a picture, at least for me, it helps more to explain things in pictures. If you're the same, then try to keep this picture in mind. On the left, you have the text, and that's the thing you can easily construct from text. You take the text, copy it many times, and always delete one more letter from the beginning until you get this triangle. These are the suffixes of the text. Ti, well, T4 is found in, well, the 5th row because we start at 0 and is naban. On the right, we get to the right by taking those strings and sorting them in lexicographic order, which we can do with a suffix tree or by constructing a suffix array. And here it is. That's the suffix array. And again, the suffix array has an entry I if this is the second in sorted order. So 7, which is the string an, because 7 is here an. That's the string of rank 2 in the sorted order. So here are the ranks 0, 1 up to 9. That's the order of the sorted suffixes. Now, where does right and left come from? It's simply if you have an entry on the right here, so you have the 8, the rank, you can go with the suffix array, and it tells you where this starts. So it goes from right to left and tells you this suffix that has rank 8 in the sorted order happens to start at position 4. And if you go on the left, that's where it is. And then the inverse suffix array is just the opposite. If you have the starting index in the text, say 0, the whole string, and you'd like to know where in the sorted order does this thing belong, what's its rank, you take R of that starting position, and that tells you where on the right you find it. So going right and left, that's what these two things do. There was a lot of time on a very simple definition, but I hope you keep in mind this right and left, leaf and rank, because that's what will pop up next. It turns out that the fast suffix sorting is much easier if you compute this rank vector instead of the suffix array directly. But it's fine, we can compute one from the other by an easy linear time algorithm. Okay, and there it is. So, well, a piece of warning before we start into this. Among all the algorithms, this might be the the toughest one in the sense that it has a couple of steps and it takes some time till we get through all of them. It's among the most complicated. I already said the KMP algorithm would be the most complicated. I think this one is easier to understand, but it's longer in the sense there's more steps to understand, whereas each individual step is not very tough. But it's definitely a breakthrough, and it's probably the most novel result I'll talk about in this module. So I hope you appreciate this. I find it's very elegant, and it's very remarkable that people came up with this. So here's, after this round of advertisement, this is the skew algorithm. It's been also been called DC3 for difference cover. We won't, it's just a name. So for us, it will be the Lineartime suffix array construction algorithm. But it's true that there are many others in the literature, and people are still working on this to get the practically most efficient of these methods. How does this algorithm work? It has 3 main steps, and they're all a little awkward. And we'll go through those one at a time. The first step says, I'll compute this rank array, but I only look at suffixes that start at positions that are not a multiple of 3. So you take your text, or you take rather this list. Now 0 is a multiple of 3, 0 times 3. So this one we wouldn't take, but this one, this one, this one not, this one, those are the ones that are included in R12, right? Not this one, this one, not this one. That's what it does. It says take those that don't start at a multiple of 3 and recursively sort those. Now recursion is always a little magic until you see what actually happens. It's hard to believe that it works, but we do reduce the input size, so there's hope, right? We only look at 2/3 of the input. This will look at 2/3 of the suffixes. Oops. So the input gets smaller. Now the tougher steps, the ones that actually do something, are 2 and 3. So let's look at number 2. 2 says if we have R12, the ranks of those suffixes that don't start at a multiple of 3, we can actually from that induce the rank array R3, which only contains those starting at multiples of 3. So all the other ones. And the trick will be we can do this in linear time using what we found for R12. Now we have 2 sorted lists. We have the sorted suffixes that don't start at a multiple of 3. We have the sorted suffixes that do start at a multiple of 3. The last step is to simply merge them, like in merge sort. So this merge is the very same thing as we did in merge sort. But we'll have to be careful that the comparisons don't take too much time. So as we'll show over the next couple of slides, both of these will take linear time. So the total complexity is a loop. We start with n. So well, assuming this complexity. So we should put a theta class around this whole thing. So there's some constant that we ignore, but say these 2 steps take n steps, then the recursion will be on an input of size 2/3 n, because we only take 2 out of 3 of the indices, and that cost is again steps 2 and 3, one recursive step down. But also this recursive step has another recursive step which takes 2/3 of the 2/3 n input, which is 2/3 squared n. And that one has a recursive call, and so on, until we finally have primitive lists of 1 or 2 elements. Now if we continue all the way up, we can upper bound this sum with this geometric series, and if you evaluate that use Wolfram Alpha or go back to your discrete math class, you will see that this is theta of n. So what remains to be shown is this. That's the crucial part. We have to show that these steps 2 and 3 can be done in linear time. And okay, a last thing is we compute R instead of L, but we can use a simple linear method to compute one from the other. So whenever we have one, we can assume we also have the other one. So we can go left and right. Let's look at step 2, inducing the ranks. So at that point, remember we use recursion to compute R12, which is the ranks of the suffixes that start not at a multiple of 3. Now step 2 tries to, so that's what I just said, formulated again. We have computed this array which stores the rank of the suffixes among those that are not at a multiple of 3. And the way I write it here is there will be an entry like R1, 2, 3. There's an entry for that, but it's undefined. All right, so this array always has 2 numbers and then an undefined. That's just for convenience. And now we're supposed to sort these suffixes and do that in linear time. How should we be able to do this? We don't know anything about these because they started at other positions than those. Well, but they're all suffixes of the same text. And that means we can actually use this information that we learned. And for that, let me draw a picture. So say this is T0, the entire text. And we also need T3, it's a little shorter. Our task is to compare those two. For now, let's ignore that we also have to sort it. Let's focus on a single comparison for now. Well, they will start with some first letter, and if the first letter is already different, we know what to do. But the interesting case is if the first letter is the same. But then, if the first letter is the same, their order is determined by whatever comes after the first letter. And that in this case is T1, and in this case is T4. It's just the suffix that starts one character later in each case. And T1 and T4 are both not a multiple of 3. So T1 and T4 are in this set that we've already sorted. So we can just look up their ranks in this set and compare the ranks instead of the suffixes. That's the key trick, what we do. And written formally, that means T0 comes before T3 in lexicographic order if and only if, as a pair in lexicographic sense, the first character and the rank of T1 comes before the pair first character of T3 and rank of T4. If you generalize this, you get a sorting method, and this is what I want to show you by example here. So we used to have our banana band, but it turned out for this it's too small, so we have Hannah Band's Bananas Man. And just to be generous, we append a couple of dollars here. That makes a few definitions smoother. Now the recursive part, so from step 1, this is where this comes from. From step 1, we get all the suffixes sorted that do not start at a multiple of 3. 1, 2, 4, 5, 7, 8, etc. That's the same picture that we had on the inverse suffix array slide. Here are the suffixes like they appear in the text, and here they are in sorted order, and that gives us the rank array. And here are the guys that we still have to sort. These are the ones that do start at a multiple of 3, and we would like to know their order. So as you might be able to see, I've split off the first character of these guys here. And if you do that, you see, well, all of those start with some character, and then comes a suffix that we find in this list. Because if I start at a multiple of 3, if I chop off the first character, if whenever I is a multiple of 3, I plus 1 is not a multiple of 3. So we can always take this remaining part, find it in this list, and translating it to its rank using R12. So we replace the whole suffix, the whole S-man $, we will just replace it by the number 14, which is the rank of this suffix in R12. And we do this for all of them. Now the important thing is that between the objects up here, the whole strings, and these weird short strings, we have not changed the order. Because if something here comes before something else, it would also be before this one here. Either because the first character determines the order, or if they are the same, the rank determines the order. And the rank was constructed from the sorted list over here. Okay, now this is one of the points where I would really like to see your faces and see how well you could follow this. But I guess it doesn't make sense to ask you for feedback on the live chat every minute. So I'll just assume my explanation was good enough. And I hope you can go through the example if not. What we'll do now is take these things and sort them. As I said, the order here is the same as the order up there, and we'd like to sort those. So we can just as well sort these guys. And if you do that, you get this order, and from that you can determine just the ranks are 0 up to 7 in the order that these things appear here. The last question for this slide is, how can you do this sorting step in linear time? Because that's what we have to do. And it turns out that in this case, these pairs that we have can be sorted in linear time by 2 iterations of this counting sort method that I've shown you. Now in general, radix sort, what I wrote here is essentially this idea: do counting sort but a couple of times. If you've seen that before, that's great, then you will understand what I mean. If not, that's not so important. The important thing is it's built on counting sort, like we've discussed it in Unit 3. And with that, we can sort these pairs, first character, rank, in linear time. So we obtain the ranks for all the suffixes that start at a multiple of 3 in linear time. And that was step 2. So step 2 of the skew algorithm takes linear time. What we're left with is step 3, which is the merging of those 2 lists. So we have the the R0, which gives us the sorted order of the suffixes that start at multiples of 3. And we have the R12, which gives us the sorted order of all the others. And what we'd like is to merge those 2 sorted lists. We know how to merge. We can use the standard merging procedure that we've used for merge sort. But the important part is that we have to speed up comparisons. If we just went on doing the string comparisons naively, we could take quadratic time, linear time for each comparison. So that's not what we can do. But we can be smarter than that, and a similar trick as in step 2 will work. So suppose we're somewhere in the merging. We started merging from the top down. Now we found, okay, this is the overall smallest. Then came one of the other list. Then came this one and this one. So what we know at this point is we've seen these ones are already sorted, these ones are already sorted, the next ones are those 2. So we have to put as the next element here, whichever of the 2 is smaller. Now we can inspect the strings and see that T11 should be the next one. But how can we figure this out in constant time? That's the important thing. So we can do the same trick that we did before. We write those 2 strings and then we split off the first character. And if we do that, we get to just the next suffix, T16 instead of 15, T12 instead of 11. In step 2, that was all that we had to do, but here we end up with a blue and a green one, and we don't know how to compare a blue and a green one. That's where we started with. So shoot, this didn't work. The trick is, one step might not be enough, but 2 steps always is. If we take the same ones, the ones 16 and 12 that we were left with, and we just do one more round of splitting off, then we reach 2 blue ones, and we know which one is big, which one comes before. 13 comes before 17, so 12 wins against 16, which means 11 wins against 15, as we've had. So the next, okay, I didn't show this here, but so the next one would be the T11. All right, let me repeat this again. Whenever you take 2 elements from the blue and the green sorted list, you can compare them in constant time by either splitting one character off, and then you always get 2 blue ones, or you split 2 characters off and you get 2 blue ones. One of the 2 always works. If you don't believe this, try to go through the different cases. There's just 2 or 3 of them. This always works. It's just the magic comes from this list being big enough, using 2/3 instead of splitting things in half as you often do with divide and conquer. With this trick, we can compare any pair of a blue and a green suffix in constant time by going at most 2 steps down. And that means we can overall merge in linear time. Remember that merging itself was linear time and used a linear number of comparisons, and now each comparison is constant time. So there we go. That means also step 3 is constant time. Together we've shown this, and that meant the overall function needed just constant time. But there is a problem left that I guess the way I presented it, you might not have noticed, but if you think about this more deeply, you will see that we cheated. In step 1, we said compute the rank of those suffixes that start not at a multiple of 3 recursively. But that's not a recursive instance of the same problem. What we need for a recursive call is a string, a single string that we compute the suffix array for, or the rank array, say. But what we're asking here is just a subset of the suffixes, just some of the indices, and not all. That doesn't work. We can't really recurse in that sense. We need a single string. How can we construct a string that skips certain suffixes? That's something we'll still have to look at. Now, it's 7 minutes left. I won't be able to go through this, so I guess I have to stop with this cliffhanger, and we'll continue tomorrow then.